In this video, I am going to explain method to determine Nuselt number, and for that we have to determine the heat transfer coefficient, and to determine that thing we have to determine the bulk temperature or mixing cup temperature. So the first of all, let me give you idea about the mixing cup temperature. This is a very important concept here. So as you know that the Newton's law of cooling states that the Q or heat transfer rate is equal to convection heat transfer coefficient into wetted area into Ts minus Tb. So let's say we have the pipe here. Okay. And we have some thickness on the wall, and we have applied some heat transfer Q, that is 50 watts per meter square. So basically this will heat up the heat up the fluid which is inside. Okay. So we know this thing that this will definitely is going to heat up the incoming fluid. And for that, the Q is already known, which is, if I define this equation as Q upon A, this is Q small is equal to H Ts minus Tb. And from here, we have the Q divided by Ts minus Tb. The Ts is the surface temperature that we can find out from the simple variable that is known as the wall temperature in the fluid. Okay, but the idea of the Tb, that is bulk temperature, mixing cup temperature, is little bit complicated. So now let's say if I make a one plane here, okay, and definitely some fluid is going through this whole plane. Okay, and on this plane we have the variation of the flow rate, and because of boundary layer, and also we have the variation of velocity, and so the variation of temperature. So there are different temperatures on different locations. Okay, now since we have to subtract the Ts from the some reference temperature that is known as the bulk temperature or mixing cup temperature, so this temperature should be a value that should not be changing from case to case for the same conditions. So if I take this temperature as a reference temperature, you take this temperature as a reference temperature, so we get the different values for the heat transfer coefficient. So this is what we don't want to do. So we have to have the some quantity that is not changing, and that concept is known as the mixing cup temperature or the bulk temperature. So now just take a look here. Now there's some body here from where we have the hot fluid is going through. So if you take a plane, this plane here at x is equal to x naught, so there is a variation of the temperature along this whole plane here. But if you pour this whole fluid into the cup and mix it very well, and make sure that the boundaries are adiabatic, means there is no heat transfer taking place from inside to outside or outside to inside. So this is not allowed here. So everything whatever is inside will have the inside. So after a certain time, if you mix it very well, the whole fluid will have the one single temperature. This is known as the mixing cup temperature or the bulk temperature. This is the whole idea of this thing. So again, for example, here I have drawn the temperature profile, and you can see temperature varying from different positions along the diameter of the pipe. So if you average this whole quantity, you get the T mean or the T bulk temperature. This is the whole idea. Okay. So mathematically or physically, what it does mean is that mixing cup temperature is an average temperature of some volume region, usually adjacent to area of interest. So in the more details, this means that if the pipe were broken at any X station and allowed discharge into mixing cup, the enthalpy of the mixed fluid in the cup would be equal to the average enthalpy of the fluid flowing through the cross section, and the temperature of the fluid in the cup would be the Tb or bulk temperature. So mathematically, this means it's a ratio of the rate of flow of enthalpy through a cross section divided by the rate of the flow of heat capacity through a cross section. So mathematically, this means that this equation, the enthalpy rate would be m dot is the flow rate, m dot into h, enthalpy, and enthalpy is defined as CPT. Delta H would be CP delta T, and H has a unit of joules. Temperature has a units of the Kelvin, so Cp is joules per Kelvin. And if we talk about the specific enthalpy, then the Cp will be having units of joules per kilogram Kelvin. Okay, but right now we are talking about the simple Cp value without the division by the mass. So we have this thing. So this is the m dot h, and divided by the heat capacity. Heat capacity is always for the volumetric flow rate. So this would be equal to the Cp. So definitely the Cp is h upon T. So h upon T. If you cancel m dot h dot, you would get the T in the numerator. This so unit would be temperature. So TB definitely has having units of the Kelvin. Okay. So now to try this equation, let me show you this thing over here. Okay, so we have the equation that says this is a m dot Cp, and in the numerator we have the m dot h. Okay, so I can write down this equation as rho Av, and the h I can write down as Cpt divided by rho Av and into Cp. Okay, so I can write down this equation as, for example, Cp rho, and because the velocity on the any cross section would be varying in the fluid, so definitely this is going to be the variable, and so is the case of the both are variable at different points. So the u and t are the function of the position x and the y, so they are variables. So that's why I am putting them inside. So they are the small u and the t, and this area, because this is for the a cross section, this is going to be the dA. So if this is for the very thin strip, this is the diameter, the dA would be equal to circumference. But if you take a strip with the some length, this is going to be the dA would be equal to circumference, which is the pi d into dx. Okay, so pi d into dx, d is the diameter of the pipe. But for the very thin strip that is having the zero thickness, the dA would be equal to pi d. Simple. Okay. So it's a very simple thing here. So you can take the dx as a very small area here. Okay, so that's why I'm going to integrate this over the whole area. So this is the dA, and definitely to integrate, if I put differential to counter the differential, we have to put the integral here. Okay, and divided by rho a u Cp. Okay, let me choose some other pen. Okay, so from here this Tb would be equal to, so now the Cp and the density, they are constant, they are not function of temperature or the pressure. So I can keep the u and t inside, and here this is the rho and Cp, and this u is going to be the average velocity at that particular location, that is the capital U, and this is the area. Okay, so now we can cancel out these terms, and we get 1 upon UA into integration UT dA. Okay, in the fluent, when we are going to go into inside the fluent, so in the fluent what is happening is that if you take the area average, this is basically an integral, and this is given by the 1 upon area and some function dA, and this phi in our case is equal to u into temperature, velocity into temperature. It means that in the bulk temperature, when we find it, we have to divide by the velocity by area. But this integration in the fluent already divides your value by the area. So what you have to do is that you have to find the average velocity, and this integration, that is the 1 upon A area integral of u t dA. This is the known as the area average, area weighted average. So this is the integration basically. Okay, so this is the whole concept of TB. And if you take a look here, you can see this is how we define here. This is equal to this value. And now we can write down the Newton's law of cooling as Q is equal to H at Ts minus Tb. And from here we can find out convection transfer coefficient as Q upon A into Ts minus Tb. And this capital Q, which is watts, and area, which is meter square. So watt per meter square is a heat flux, that is the watt per meter square. So we can write down as a small q divided by Ts minus Tb. Okay. So now we have to determine the values of these variables. Okay. So the procedure is given here, but I will show you here. So the first thing is that we have to create a isosurface. Okay. And where we have to create it near to the outlet. Why? Because maybe in the 10 meters, in the first 20 meters, we allowed the flow to develop hydrodynamically, and the last 10 meters, we should allow the fluid to develop thermally. So that's why we should be taking values at the end of the pipe. So this would be around 29 and 30. So between 29 and 30, but close to outlet. So I'm going to make the one isosurface. This is going to be the one area region. Okay. And this is, let's say we take it 29.8, almost close to, very, very close to outlet. Okay. So let's say I call this as surface, and okay, mesh. Okay. This is Z coordinate. So this is going to be the 29.8 surface and create. And second thing we want to create is a line, a circular line, circumferential line, on which we will be finding out the surface temperature. And that we create from heated wall. Again the same thing, but this heated wall is from 20 to 30 meters. And again, but the units are same, 29.8. And this time this is the line. So surface and the line. If you display this thing, if you display this mesh, you will see that this thing is over here. So I display outlet, line and surface. Okay. And also edges. So you will see this line is over here basically. And the whole surface is over here. So on the surface we are going to find out the bulk temperature, and on the line we are going to find out the surface temperature. Then we put this thing into the equation where we have to divide. We have to put the numerator as the heat flux, divide by the Ts minus Tb, and we get the heat transfer, convection transfer coefficient. Okay, so we have done this thing, and now we have to define the one variable, custom variable, and that is a variable of velocity. So select, multiply by temperature. So function of velocity and temperature. So velocity and temperature, define. And then go to results. From here, surface integral. And I told you that the area weighted average is the integration of the whole those variables divided by the area. So custom field function is the velocity and temperature. We have to select this surface and compute. Okay, and then on the circumferential line on the same location, we have to choose the velocity and compute. Okay, and then we have to use the vertex average. So for the temperature, we are going to use a vortex error, but you can also use the area weighted average. So we are going to determine the wall temperature and compute. Okay, sorry, this is divided by the area, so we have to multiply by the area. So I think the better method would be use the vertex average. This is the, oh sorry, it should be line 369, and if I choose area weighted average, this is 369.175. So there's a little difference, and here we were making the some mistake. So because we were choosing the surface, so it should be line. Okay. So now if you take a look on the formula, you can see that we have to use this formula. Okay. So the TB is this value. So from the calculator, we have to divide this integration. This integration is over here, this whole divided by area. So this value is 45 point, this value is over here, 45.24, 240963, and divided by the velocity, average velocity on the whole plane. This velocity is 0.14550502. So this becomes 310,923. Okay, let me open. Okay, I will do this calculation over here. Okay, so the bulk temperature one minute. Okay, so Microsoft whiteboard. Okay, so the bulk temperature or mixing of temperature is equal to 310.9237 Kelvin. Okay, so and also we determined that the surface temperature is based on the vortex. So TS or surface temperature is 369.28078. Okay, and we have the formula from Newton's law of cooling that the H is equal to Q upon TS minus TB. So Q is 50, and if we divide by this value, this is 369.28078 minus 310.9237. So subtract from this value 078. So 1 upon this value and multiply by 50 heat flux. So we get the heat transfer coefficient value as 0.85679 watts per meter square Kelvin. Okay, and now for Nuselt number is defined as heat transfer coefficient into diameter. Usually speaking, in the formula they write down small d, but we use d, capital D for diameter, but I will use the same definition here and divide by the K. This is the thermal conductivity of the fluid, not the material of pipe. This is the thermal conductivity of the working fluid, that is the air. And for air, this is 0.0 0.02, 1 minute. This is 0.0242. Okay, and different units are the watts per meter Kelvin. So I can put the values over here. This is going to be equal to 0.85679 into diameter is equal to 1 divided by 0.0242. So if I divide this value by 0.0242, so we get Nuselt number as 35.4, and this is non-dimensional number, so there are no units for the Nuselt number. Okay. Now similarly we have to use now Dittus Boelter equation, and this equation states that this is equal to this form. Okay, so now this is the Nuselt number from CFD, and from the correlation, if I find out this value, so we have the Nuselt number will be equal to 0.023 into 10,000 power 0.8, and the Prandtl number value for the air is around 0.714, but you can use 0.71 power 0.4. Okay, so now 10,000 power 0.8, and open second calculator, and 0.71 power 0.4. So this value is 0.817 something. So select all and copy and multiply here, and Control V, paste, equal to sign, this value is this one. This is a multiplication of these two terms, and now multiply with 0.023. So we get the value of Nuselt number from the Dittus Boelter correlation as 31.785. Okay, this is from Dittus Boelter correlation. And please keep this thing in the mind that this correlation is valid for a Reynolds number greater than 10,000. It means that we are almost at the edge of its validity. So below this value, this is not valid. So maybe if you go with maybe 30,000, 40,000, you will get maybe more close values. Okay, so now we can find the percentage error in both values. So this is from CFD is equal to 35.4 minus 31.785 divided by 31.785 into 100. Okay, so minus 35.4 and divided by 31.785 into 100. So error is around 11.3%. It's not a very bad error. Okay, so this is the whole procedure to find out the heat transfer coefficient, bulk temperature, the heat transfer coefficient, and then Nuselt number, and then from the correlations you can find out the values in this way, and then you compare them in this way. Okay, so I can show you now the slide where we have the very neat and clean values. Okay, so from CFD we have the Nuselt number 35.56. From Dittus Boelter correlation we have the 31.78, so error is around 11.8%. There are some differences because of the round off errors, so just ignore this value.